Here we go. All right, in this question, question 3, we're going to start off by defining electric field strength. Let's call it E for electric field strength. E stands for a lot. Remember, it's like Young modulus, energy. So like in this context, 2 ways to think about electric field strength. And really the better way to define it is this one. But if you're thinking about like, what equations do I know for this? Force per charge, volts per meter. So voltage per distance, which are the units, volts per meter, measure electric field strength. They're equivalent, a volt per meter is equivalent to a Newton per coulomb, a Newton of force per coulomb of charge. So if we kind of use this equation to put it into words to define it, we can say the electric field strength is the force acting on unit, and let's remember, positive charge. The electric field has a direction. If you look down here, you can see that these arrows are pointing, to the left. And so that's showing us the direction of the electric field. It's the direction that a positive charge would move, a proton. Note that the electron is negatively charged and it's moving the other way, right? So that kind of reminds us, oh yeah, electrons move against the direction of the electric field because the electric field direction is defined as the way a positive charge would move. So the strength of the electric field is the force acting per unit positive charge. Easy to forget that, but remember that it's essential to get sort of the direction of the field also within the definition. As mentioned a moment ago, we got an electron and it's accelerated from point A to point B by a uniform electric field, as illustrated in this figure 3.1. The distance between A and B is 12 millimeters. There's a metric prefix. The velocity of the electron is 2.5 kilometers per second at A, and at B, it's 18 megameters per second. Metric prefix, metric prefix. Calculate the acceleration of the electron. So acceleration is just the rate of change of velocity. So the change in velocity divided by time. It looks like the final velocity is 18 megameters per second. So 18 times 10 to the 6. This capital M means million, 10 to the 6, minus the initial velocity, 2.5 kilometers per second, over a distance of 12 millimeters. They make that. So it's not as straightforward as just, oh, here's the time. They give us, the distance that it covers. So we're going to have to deduce the time. Or we just say, forget all this. We'll figure out the acceleration some other way. So if you don't know time and you don't really care about it because we don't, we could solve for time and then plug it back in. We don't have to be so quick to give up on this. This is a path forward, but it requires us to use another equation to solve for time first and then plug it back in. When we've got an equation like this at our disposal, we can relate the final velocity to the initial velocity of something being uniformly accelerated over a given displacement. And so because we're solving for A, it's the only unknown in this. We know that the displacement is 12 millimeters. We know that the final and the initial velocities are 18 megameters per second and 2.5 kilometers per second, respectively. So it's perhaps a more elegant path to the solution to just use one equation and solve for A. But, you got squareds in there and, maybe it wouldn't have been too bad to just, think of another equation that allows us to solve for T here and then plug it back in. For completion's sake, I will solve it both ways and we'll compare our answers there. So let's get rid of that. First, I'm going to solve it this way. It's going to look like this. Acceleration equal to the velocity final squared minus the initial velocity squared over 2s. So everybody good with that little bit of algebraic manipulation, making A the subject over here. So I just subtracted this from both sides and divided by 2s. Got this. Now I'll substitute in 18 megameters per second squared minus 2.5 kilometers per second squared over 2 times the displacement was 12, and then milli is 10 to the negative 3 meters. So this will give us meters per second squared. All right, in the numerator, I've got 18 by 10 to the 6 squared, so 3.24 by 10 to the 14, minus 2.5 times 10 to the third squared equals, so 3.23999 by 10 to the 14. So it's kind of like this. This is pretty negligible compared to that. Now I'll divide that by, let's see, it's going to be 2 times 12 by 10 to the negative 3. So that's the same as 24 times 10 to the negative 3, right? Equals. So I'm getting here 1.35 by 10 to the 16 meters per second squared. That's a lot of G forces. So we're feeling like 1 G force is 10 meters per second. So like 10 to the first power, 15 orders of magnitude more acceleration. Well, it's just a tiny little electron, right? So that's a lot of acceleration. Let's see how we could have solved it this way. You may recall that there's a way to think about acceleration with no acceleration necessary. It's kind of like the displacement equals 1/2 u plus v t. This is like saying something sped up from u to v, over time t, and we're just sort of averaging it. So remember, when we derived this equation, we sort of took an object that was increasing its velocity from u to v over time t. And so we'll just average it out, u plus v over 2, right? So it's u plus v over 2 times the time. And so it's a way to just sort of say, well, it had an average velocity of right in between these two, right? So it's sort of averaging the initial and final velocities and then just timesing it by time. That's a perfect way to calculate the displacement. We know that the displacement is 12 millimeters, right? And so we could calculate 1/2 the initial velocity, 2.5 kilometers per second. 2.5 kilometers per second plus 18 megameters per second times t, and then see how we can solve this for t here. So let's try that out and see what we get. So I've got 18 times 10 to the 6 plus 2.5 times 10 to the 3. That gives me 1,800,000 18,002,500. Right, 18,002,500. What's 18 million plus 2,500? 18,002,500, of course. And so that's the sum of those two. And then I'm going to multiply that by 0.5, right? Because it's 1/2 the sum of that times t equals that. So now I have sort of on the right side of this, I have this 12 millimeters equals, I just calculated all this, the sum of these two times 1/2. So this is 9,001,250 times t equals 0.010012, right? That's this. So now I take my 0.0012, my 12 by 10 to the negative 3. Oh wait, let's make sure I'm not making a mistake with that. 12 times 10 raised to the 3 negative. 0.012, yeah, because it's 12 times 10 negative. So this is 0.012, I'll write the first time, 0.012 divided by 9001250 equals. So this electron from here to here, it's like, come on, electron, we got places to go. You're taking forever. You took all of 1.33 times 10 to the negative 9 seconds. So, hey, since we're doing like all our metric prefixes, we got kilo, we got milli, we got mega. Let's throw in a nano. Why don't we? Why don't we just say that's 1.33 nanoseconds, right? 10 to the negative 9 is a billion. So this electron traveled 12 millimeters in 1.33 nanoseconds. All right, it's going 18 million meters per second by the time it got here. So this is our, 1.33 by 10 to the negative 9. Remember, we just solved for the time. So now we could, that was one way to get to the acceleration, right? All you got to do is figure out the time first. We didn't need to know the time. Maybe they ask us to calculate it, in another one. So I've got now my difference in velocities, 18 times 10 to the 6 minus 2.5 times 10 to the 3 divided by 1.33 times 10 to the negative 9 equals, and I get 1.35 times 10 to the 16 meters per second squared. So indeed, any paths to the same correct solution. Which way do you prefer? Would you rather just use one equation that's got some exponents in it, but everything is given? Or would you rather really sink your teeth and find out some extra information, like how much time does it take there? Sort of practice with this equation, substitute it back in, just the definition of acceleration, right? Rate of change of velocity gets you the right answer either way. Let's keep going through. It says calculate the change in kinetic energy of the electron. The change in the kinetic energy of the electron. All right. So everybody good with all that working? Great. What's the change in kinetic energy? Change in kinetic energy is the kinetic energy final minus the kinetic energy initial. The final kinetic energy would be 1/2 mass times the final velocity squared. 1/2 mass times the initial velocity squared. Okay. We could factor out the 1/2 m. 1/2 m times v squared minus u squared, right? That's the same as that. And then we can make some substitutions. 1/2, anybody know the mass of an electron? (9.11) times 10 to the negative 31. No, I'm not having one of those bad scroll bar getting away from me. I'm actually on purpose going up here to the formula to show you that, hey, there was that v squared equals u squared plus 2as. So that equation is sort of given. But if we go up further still, computer cooperates, we can find the rest mass of an electron. And now you might say, well, it's not at rest. This electron was going 2.5 kilometers, per second and 18 million, meters per second. But this is the way that we're going to solve it. Okay, so we're just going to say, well, but that's only when we get really close to the speed of light. And even though 18 megameters per second is pretty fast, it's not that close to the speed of light. So we'll just kind of use the rest mass of the electron there as the mass. Okay. All right, so we've got the 1/2 m factored out, and now we got to multiply it by this term. So we're substituting in now the final velocity, which is 18 megameters per second squared minus the initial velocity, which was 2.5. Oh, that's not better, that's worse. Sorry, everybody. (1/2 m 9.11 by 10 to the negative 31 kilograms times v squared 18 mega, so 10 to the 6 meters per second squared minus 2.5 kilo 10 to the 3 meters per second squared, right? So we have to square the velocities. All right, so sort of working in the brackets first, I've got my 18 times 10 to the 6 squared. And subtract from that minus 2.5 times 10 to the third squared. So the difference, remember that we had to calculate the same sort of difference the way we did the, we used the equation v squared equals u squared minus 2as. We'll sort of subtract from both sides. So we have this 3.23 times 10 to the 14. That's sort of what I get for the difference between these velocities squared. Multiplied now by, I'll do the half first, times 0.5 equals, and now the thing that's going to really sort of reduce this, right? So the change in kinetic energy, because the electron is so low in mass, that even though this is like 10 to the 14, 10 to the negative 31, right? That's sort of the dominant factor there. So now we're going to multiply by 9.11 times 10 to the negative 31. Give us a final answer of 1.5 by 10 to the negative 16 joules. That's the change in kinetic energy. If we were to calculate like what is the kinetic energy in joules, of an electron that's even going, 18 million meters per second, again, because the electron is so low in mass, that's a very small amount of joules. And so the change is tiny, because a joule is a pretty big unit of energy. That's why we use electron volts, when we're talking about sort of tinier energy. All right, now we need to calculate the electric field strength. So we started this by considering the definition of electric field strength. And now we've sort of done some calculations along the way. Now, voltage divided by distance, they don't give us anything sort of about that, towards that path to the solution. So they don't tell us like it's hooked up to a EMF with this, potential difference. They don't give us a clue about the distance between the plates, right? Sort of like where we're creating the field. They only tell us the displacement of the electron that's moving along the sort of the, within the field. To reinforce and emphasize what I'm saying, if you look at the schematic of this electric field, this field is created sort of between, let's just imagine the plates are sort of like here and here, right? So that there's like a positive plate this way, repelling protons this way. They're attracted to the negative plate over here. So we don't know the distance between these plates. We just know that from A to B is 12 millimeters. So we can't really rely on this form of the equation to figure out what the electric field strength is. We have to sort of reason our way through it this way, force per charge. Let's think about what we know there. All right, electric field strength, force per charge. Don't forget that the change in kinetic energy was this, okay? 1.5 by 10 to the negative 16. We just calculated the change in kinetic energy was 1.5 by 10 to the negative 16. Now, if you think about why did I just do that? Why did I calculate the change in kinetic energy? And now they want the electric field strength. Doesn't one calculation lead to the next? What's the roadmap to get from this answer to that answer? Well, what do we know about changes in kinetic energy? One of the things that might come to mind is work, kinetic energy theorem. Work is the change in kinetic energy. Because an object in motion just remains in motion on its own in a straight line until some net force acts upon it. Well, when a net force does act upon it, right, over a displacement, you've done some work to it. And that's going to be the thing that changes its kinetic energy, that speeds it up or slows it down. So things don't just speed up or slow down on their own. Forces are required to do that. And the force acting on the object over a displacement, when the force is in the same direction as the displacement, the product of those two vectors is work. And work is the change in kinetic energy. Okay, so we already know the change in kinetic energy. 1.5 by 10 to the negative 16 joules. We know the displacement over which this change in kinetic energy occurred. That was 12 millimeters, right? So 12 millimeters times some force equals a change in kinetic energy. Kind of nice to remind yourself of that. Work kinetic energy theorem relates what we just calculated to something that's going to help us solve this. Because remember, we want to know the electric field strength, and we've sort of given up on this with, oh, there's really no way to sort of figure out the voltage here, right? But maybe there's a way to figure out the force per charge. Just like we can look up the mass of an electron, you could look up the charge of an electron, the elementary charge that's up in the data table, but hopefully you know that elementary charge is 1.6 by 10 to the negative 19 coulombs. So there's our per charge. We know it's a single electron in this field. So as soon as we figure out the force with this very solvable algebraic equation, we just plug it in here and bingo. And note that they give us this volts per meter. They give us the units sort of this, which are equivalent to a Newton per coulomb. And we can kind of show that too if we want. Let's divide each side by 12 millimeters. A joule per meter is a Newton. So we'll plug in this answer up here. All right, I've got my 1.475819972 by 10 to the negative 16. So I got like this full unrounded value in my calculator. So it should be close enough. I'll just leave it. So in other words, your answer, if you're typing this into your calculator and dividing by this, might be a little bit different from mine because I still have this value in my calculator from this. So like, again, one calculation leads to the next. And I'm taking this number and dividing it by the displacement. So divided by, open parentheses, 12 times 10 to the negative 3 equals, and I get a force of 1.23. 1.23 times 10 to the negative 14. If the force of 1.23 by 10 to the negative 14 newtons is acting on a charge of 1.6 by 10 to the negative 19 coulombs, then I can deduce the electric field strength as the ratio. So again, one calculation leads to the next. Now I've got this number in my calculator, but it's actually 1.229849976 by 10 to the negative 14, divided by, open parentheses, the elementary charge, the charge on either an electron or a proton, negative or positive respectively, but we don't really care about the sign too much. So divided by, open parentheses, 1.6 times 10 to the negative 19, and that equals an electric field of 76,865 newtons per coulomb, which is a volt per meter. And let's just call that 7.7 by 10 to the 4. Right, round that up to that decimal. All right, moving right along here. Now we've got an alpha particle moves from A to B in the electric field. Describe and explain how the change in kinetic energy of the alpha particle compares with that of the electron. Numerical values are not required. All right. The change in kinetic energy of the alpha particle. So there is a certain field strength, 7.7 by 10 to the 4 volts per meter. That's the strength of the field. Remember what that tells us. That tells us that there is a force acting on the charge there. So if we multiply both sides by the charge, then you sort of get the force that each thing is sort of experiencing. And so an electron has a single elementary charge. It has sort of like 1 E. But the alpha particle has 2 charges. The alpha particle, an alpha particle is a helium nucleus. And so we've got something that has 2 protons and 2 neutrons, right? And it's just that, the nucleus sort of the helium atom. So there's no electron cloud or anything, no orbitals to worry about. It's just 2 protons. So just like I mentioned, that elementary charge is the charge on either an electron or a proton. It's just negative or sort of positive. We've got 2 protons in this alpha particle. And so if we multiplied, sort of to calculate, well, what's the force that a charge, is going to experience in a given constant electric field? We have this value that's fixed, right? There's a certain electric field, and that's the value of it. Multiplied by the electron's charge, we got its force. Remember, it was like 10 to the negative 12. That's what we had to actually plug in to solve this. We figured out the force from using work. Work is the change in kinetic energy. Now we're sort of asked to think about, sort of, well, what would happen to the kinetic energy of an alpha particle? Well, we'd have the same field, this strong, but now we multiply it by 2 charges, right? In other words, it's going to have twice the force now. So an alpha particle in that field is going to experience twice the force because it's the electric field is like the force acting on unit charge. So we got 2 unit charges, right? So it's going to experience twice the force. If it feels twice the force, okay, then let's go back now to work equals change in kinetic energy. And so what have we changed? We're saying from A to B, so we're not changing the displacement, that stays fixed, but now we got twice the force. Okay, so what's that going to do to the change in kinetic energy if we just doubled this now? Well, we got to double that. We're going to double the change in kinetic energy. Describe and explain how the change in kinetic energy compares with that of the electron. The kinetic energy is going to be twice as much. Okay, it's going to change its kinetic energy twice as much because the electric field is doing twice as much work. It's exerting twice the force on that particle because it has twice the charge. Okay, so you kind of want to put that into your own words. The change in kinetic energy is greater than that of the electron. It's doubled it, it's twice as much because, it has twice the charge. It will experience twice the force in the uniform electric field. Let's take a look at the mark scheme now. So we'll go back. This is question 3, right? Let's take a look at all your calculations there. Let's go through it. Paper 23. Have a look. All right, force per unit positive charge. See how that positive is in there, but it's in parentheses, so I guess they wouldn't be too harsh on you if you didn't have it. All right. 1.35 by 10 to the 16. Okay, you can see that they used this equation of motion to solve it. They didn't even bother to show you that there was another path to that solution. Changing kinetic energy, again, using the rest mass of the electron and the velocities, we get 1.5 by 10 to the negative 16. Here they've got the electric field is the force per charge equals mass times acceleration over E. So they substitute an MA for that, or charge times voltage is the change in kinetic energy. So E is the change in kinetic energy divided by E. So work, force times displacement equals the change in kinetic energy. It looks like they're sort of making a substitution for that. There you go. That's very much related to electric fields right now. So when there's not electric current passed through halogen, then the fluorescent light will not fluoresce. We'll cut off. That's the electric field strength. We got a charge on an alpha particle opposite to the electron. It's positive. Okay, so the kinetic energy, the change in kinetic energy is negative, or it's reduced. The charge is twice that of the electron, so twice the magnitude. So yeah, I guess I wasn't so mindful of, hey, they're protons, they're not electrons, so they're positive. And so indeed, it's going to sort of push it the other way. Now, because kinetic energy is a scalar, the direction sort of doesn't matter so much, but there is a way to sort of interpret, is the particle going with the direction of force or sort of against it? Just like if you lift something up, you're doing positive work, you're exerting a force in the direction, but sort of like, gravity is sort of doing negative work. When you're lifting the object down, now gravity is doing the positive work, you're sort of holding it up against gravity. So the change in kinetic energy is negative, but because the charge on the alpha particle is twice that of the electron, this causes, so I kind of focused on this last mark here. It's going to have twice the sort of change in kinetic energy in magnitude, right? Because the direction is sort of opposing it. It's negative, and so that actually means it's less, right? It's more negative. All right, so nearly perfect on that.